Alright, so this is going to be the part 3 of the multi-electron system. So in this video, I'm going to actually explain what is the atomic size, there is a periodic trend for the atomic size, and then ionization energy, defining the ionization energies, and then the periodic trend. And then I also talk about this electron affinities. What is electron affinities, and then what's the periodic trend. So starting out with atomic size, remember that we actually talk about this Z effective, and Z effective increase as you go to the right top. The Z effective is not just right? Z effective increase going from left to right, right? So as the Z effective increase, the power to draw the electron inward actually increase. Thus the outermost electron is going to be drawn toward the nucleus. For that reason, that atomic size decrease going this way. Now you can see that atomic size is going smaller and smaller, right? And that goes with the same trend. You see that there's the same trend, right? In each rows, right? And that's because of the Z effective. Now, as you go down in the periodic table, then you're adding sort of like an onion shell, outer onion shells, right? So, for example, like lithium right here is a 1s squared 2s, right? And then for the Na right here, Na is a 1s squared 2s squared 2p6, and then you have this 3s squared, right? So a whole bunch of stuff is inside, right? So that's a N right here, and also that N is getting larger, right? So as the N gets larger and larger, then it becomes it goes outward more and more as the N becomes large. So if you go down in a periodic table, the atomic size increase, and if you go from the right to left, then the atomic size increase, right? So the smallest atom is that one right there, He, the helium. And then the largest atomic size is the atom with the largest atomic size is left bottom of the periodic table. That's the largest one. In this particular one, that CS is the largest among this choice of atoms. Now I'm going to talk about the ionization energies. The ionization energy, the definition is the energy required to rip off the electrons. You're ripping off the outermost electrons. The reason why that you're ripping off the outermost electron, because that's the easiest to take it off. So ionization energy is energy required to rip off electrons from the system. For example, Na, for example, starting out with a neutral atom, and then after you rip off the electrons, it becomes Na plus and E minus, right? Notice that the charge is conserved. You start out with a total of net charge of 0. You end up with a net charge of 0 because you're producing negative charge and positive charge here, the same amount, right? So everything is conserved. But remember that these positive charge and negative charge, they're attractive, right? So as you put these charged particles closer together, the energy of the system actually decreases, right? It becomes more stable as the positive charge and negative charge are close together. So that's pretty much the case for the atom. All positive charge and all negative charge are very close to each other. But for the ion, you're ripping off the electrons away from the rest of the stuff, which is positive charge, right? So you're separating the positive charge and negative charge. So positive ion is always higher in energy than the atom, and energy required to go from atom to the positive ion is the ionization energies. So here is the ionization energy, the energy required to rip off the electrons from each atomic type. So for the hydrogen, 1312 kilojoule per mole, and then helium atom, it's 2372, right? And then there's the rest of the stuff that's listed here. You notice that in general, if you go from left to right in this table, the ionization energy increase. The reason why it increases is because that as you go to the right of the periodic table, right, these guys actually have a high Z effective. That means that outermost electrons have this effective positive charge in the middle, right? Outermost electrons see this effective positive charge in the middle. And the effective positive charge increase, it's harder for you to actually take the electrons away from that positive charge. If you have more positive charge, it's going to be harder. So if you go back to the Z effective, right? Z effective increase, right? Going from the lithium, barium, so on and so forth, right? So the N, for example, is much higher Z effective than the lithium, 1.28 and 3.83. So if you compare those two, then the that one right there is 1400 compared to the 520 kilojoule to take the electrons out from the rest of the stuff. It's much easier for you to actually remove the electrons from the lithium atom compared to the nitrogen, which is very difficult. And it gets really difficult if you are dealing with the neon atoms, because neon atoms actually have a very high Z effective. And put these things in the graph, hydrogen, helium, and then lithium, Be, B, carbon, NO, Fe, right? So all of these things are there, but you notice that there is two kinks here, like right around here and right around here. It's not trending, right? Like rest of the stuff. Same goes here, like it's against the trend, right? So what's going on here? Oh, and I should probably point out the other stuff before I actually go into this one, is that if you go down in the periodic table, the ionization energy, the energy required to rip off the electron, is smaller and smaller. The reason why it's easier for you to take the electron out, away from the rest of the body, is because that outermost electrons are far away from the rest of the stuff. So for the cesium, for example, only requires 376 kilojoule per mole to actually take the electrons off. But for the hydrogen, because electrons are so close to the hydrogen atom, it's very difficult for you to actually remove the electron compared to the cesium. Cesium like super far away, so it's just easy for you to actually take the electrons off. So I'm still not explaining this portion right here, that kink right here. So let's just go back to that one. So if you recall that energy of the atom is always smaller than energy of the ion, right? Because these are positive, negative is very close to each other, and the positive and negative super far away, right? But if you recall all the way back, there was a special case, right? It's like long time ago. Half filled and completely filled. Those are the special cases, right? The energy of the atom is stable if you actually have a half-filled orbital or the completely filled. In that particular case, right? In these particular cases, the atom actually obtains much more stable conditions. So if I apply the same topic here, and then let's just consider the nitrogen and oxygen in terms in each case here. So the nitrogen having, if you go to the periodic table right here, nitrogen have 3 electrons in a p orbital, right? Nitrogen right here. Nitrogen right here, right? So there's 3 electrons, right? So there we go, yeah. Nitrogen having the 3 electrons, that's before you remove the electrons. But wait, this is a half-filled orbital, right? So half-filled orbital, this atom, nitrogen atom, is more stable than what you expected. So the energy of the atom is actually lower than the actual what you expected. But for the ion, because you already remove the 1 electrons, this p orbital is occupied by only 2 now. There is nothing special about that one. So energy of the ions where it's expected. Now for this particular case, what's ionization energy definitions? Going energy required to go from the atom to the positive ion, right? So this gap is bigger than what you expected, right? This portion right here is what you expected, but actual case energy, actual ionization energy is much bigger than what you expected. Now for the oxygen case, you have 4 electrons in the p orbital, right? 2, 3, the Hund's rule goes like this, right? There is nothing special about this oxygen atoms, right? But what happens if I actually remove the electrons here, O plus ion? If I remove 1 electrons, then what's going to happen is that you have only 3 electrons. Then wait, that's half-filled orbital, right? So energy of the ion in this particular case, the energy is much lower than what you expected. So instead of actually having the energy here, the energy of the ion is actually lower than what you expected. So energy expected here, and this is actual ion energies. Energy of the ion, right? And then for the atom, there is nothing special about this one because it's not half filled or completely filled, so it stays the same. then the ionization energy expected is this gap. This is expected, right? But actual ionization energy, actual ionization, this is actual, is much lower than what you expected. So there is a reverse things going on with the nitrogen case and the oxygen case. For the nitrogen case, the actual ionization is much larger than what you expected, but for the oxygen, it's much smaller than what you expected. And because of this, being larger than expected, the ionization energy is larger than expected for the nitrogen, and then oxygen smaller than expected. So that's why you have this gap right here. But for the B atom and BE atom right here, it's the periodic table. So BE atoms and B atoms. So now we're talking about BE atom. This one has 1s square 2s square, right? It's completely filled. And then for the B atom, it's 1s square 2s square 2p, right? So let's just go to the let me just try to work it out here. So for the B atom right here, for example, there is nothing special about having the 1 electrons in a p orbital. So that this is a B atom, and this is an atom and ion, right? The positive negative close for the atom, and then the positive negative very far away. Some ion is always higher in energies, and atoms there is nothing special about that one. But if you, that's the 2s orbital, right? This is 2p. Now, if you take the 1 electrons out of the B atoms, then what's going to happen is that you have 0 electrons here for the p orbital. This is a B plus ion, right? You have a completely filled orbital for the 2s. So for the ion, the energy is much lower than what you expected. So the ionization energy is much lower than expected. So it's the same thing going on here. So the BE and the B, there is sort of like getting slightly smaller than the B right here, right? The B ionization energy for the B atom is smaller than the ionization energy for the BE, just because of that. So I explain this and that, and the same explanation actually works for these guys too, for any of these laws. You can actually repeat the same explanations. Now, I was always actually talk about this taking out 1 electrons for up to this point, but you can also take out like many electrons. Like for example, like I was actually talking about this kappa for many times, right? Kappa has 29 electrons, right? And you can actually remove all of those guys, 29 electrons off from the kappas. The problem is that you're gonna need $1 million, or maybe like a lot more than $1 million, and then like the instrument that's bigger than the LSW to actually rip off all those electrons from the kappa atoms. So just to give you the pictures here, is that for the Na atom, it's very easy to actually remove the very fast electron here. So this is for the Na. Na atom. Na have 11 electrons, right? And you can actually remove like 10 of those. Like first one just about requires 500 kilojoule. The second one is much more than the first one. You're gonna need 4,500 kilojoule to remove the second electrons. And if you actually remove the 10th electrons, like removing 2, 3, 4, 5, 6, 7, 8, 9, and then removing all 10 of those, right? You're gonna need that much energy for 141,000 kilojoule to remove that 10 electrons, and 11 electron is gonna be even harder than this one. So I think it's probably none out of the energies. I think not really sure exactly why they don't have this 11, but it's probably need a lot more energy than this guy. But technically speaking, you can actually remove as many electrons as you want to. The problem is that it requires more and more energies to do so. So the first one, you're removing it from the outermost electrons, and then removing one by one, it gets smaller and smaller, and then the last one is going to be the hardest one to remove. Now we're going to move on to this electron affinities here. The electron affinity is this is a strange one. It's energy released when the atom in the gas phase accepts an electron. So you're trying to attach the electrons. You're trying to attach the electrons to the neutral atom and then see what type of energy is actually released. How much of the energy is actually released to the outside. And that's really the electron affinities. So this one right here is literally a little bit of a historical reasons that the electron affinities is sort of defined in a weird way. The electron affinity, most of the case, like ionization energies, is initially you start out with neutral and then you become ionized, right? Positive later, right? So the energy, ionization energies, is actually positive because you're subtracting the energy of this ion minus the neutral. So positive ion, energy of the positive ion minus energy of the neutral. So start out with neutral and then end up with ion, right? So ionization energies, just like in all other case, energy of the final state, that's ion, minus energy of the initial state, the starting point, which is neutral. So this case, particular case, it is positive ion, and then this is negative ion. Now, electron affinity is different. I believe that this may be the only place that the changing energy, like ionization energy or any of these things, doesn't have the final energy minus the initial energies. The electron affinity instead actually have this negative sign in front. So electron affinity is it's energy released, so it's going this way. So it's really the initial energy minus the final energies. That's the strange thing about it. Initial energies, initial minus E of the final. So that's a little bit strange, but that's historically it's been like this. So which means that this one right here is actually E of atom, not because you start out with atom and then trying to attach the electrons to become the negative ions, some energy of the negative ion. So that's the definition of it. So another thing right here is that the energy of the atom is typically higher than the energy of the negative ions. More electrons you have, energies, generally speaking, it's lower in energies. But notice this. This one right here is neutral, right? Neutral. And then this one right here, you are actually separating the neutral and negative ion, right? Well, actually, this one right here is actually close, right? This one is close, but the neutral, they have this super far away distance with the negative ions. So that the atom is sort of like, it is there, but ions, you're putting those things together. So this may be like 100 kilometers away. And then you're just looking at these neutral energies. But for this one right here, you're putting those negative ions close to the neutral atoms. But notice that neutral is not even positive or negative, right? So there is no obvious positive negative interactions or negative interactions here. So what I want to say here is that the electron affinity in general have a much smaller magnitude than the ionization energies. So that these are the table for the electron affinities. And compare like these numbers, like 26 kilojoule per mole or the 122 kilojoule per mole. All of these guys in magnitude is much smaller than 1000 or 2000 kilojoule per mole for the ionization energies, because ionization energies, you're dealing with positive charge and negative charge getting close to each other, or trying to stay away from it, right? Or you're trying to rip off the positive charge away from the negative charge, and so on and so forth, right? But for the electron affinities, that's not really the case here. You have negative charge and neutral. They don't have this positive negative interactions. So that's why the magnitude of this electron affinity is small compared to the ionization energies. Now, other things that I want to actually talk about here is that any of these ionization electron affinities, if it's positive, like the fluorine right here, it's very easy for you to actually attach the electrons. That's what it means. So fluorine, chlorine, bromine, any one of these guys are easy to attach the electrons. So does oxygens too. But for the nitrogen, it's very hard for you to actually attach the electrons. And can you guess why that's the case? It always associates with that special configuration of the half filled or the completely filled. So you can probably think about that process right here. If I try to actually plot these things, then you get this more random stuff compared to the ionization energies, just because that the magnitude itself is very small, so it gets more noisier than the ionization energies. But the typical trend is pretty much the same in a way. I shouldn't probably say that it's same, but it's these guys right here for the electron affinities. I remember that these guys very easy to put the electrons on. That's what I remember, and the rest of the stuff it's too small, and then I just need to go back to the table and then look at what's going on here. It's just too noisy to tell you what's happening in this one. Alright, I think that's probably all I wanted to say. You can also work on this particular example, like for the example, like if I actually have this lithium atom. For the lithium, you have 2s. There is only one electron, right? So if you want to actually put one more electrons here, that's going to produce a completely filled electrons. So there is an atom, and then this is a negative ions, right? And then this negative ion achieves a special configuration which is completely filled. So electron affinity for the lithium is large here. Right here. But for the B right here, if I start out with the BE atom, then for the BE, you start out with this particular configuration, so the atom is actually lower than expected. But for the ion, the p orbital, 2p orbital, there is nothing special about that one, so it stays the same right here. Then the actual ionization energies, not ionization energies, electron affinity is much smaller than expected, and that's why that BE is very small compared to the lithium. And so these type of things, it's still there, but I wouldn't say that it's as obvious as the ionization energies. Electron affinity is slightly more noisy, just because that we are not dealing with the positive negative interactions. So that's pretty much all I wanted to say about size of the atoms, or the trend in the size of atoms, and then the ionization energies, and then electron affinities. You have to remember what is the definition of the ionization energies, and you have to remember the definition of the electron affinities. One is to remove the electrons, and then one is to attach the electrons. And then for the electron affinities, it's the energy released outward is the ionization energies. So the positive number right here means that it's easier for you to actually attach the electrons. It's good enough.